I'm Anil Kumar. Welcome to my YouTube channel and the website globalmathinstitute.com. We now have around 20,000 videos on YouTube, and as per your request, I'm now trying to organize them into this website. A lot of resources have been utilized in doing this development work. By now, 7,000 videos have been attached. However, because of the lack of funds, our progress is really slow in coming up with the completely usable website. Now, our approach here is to provide you with integrated solutions to the questions, which should definitely help you to get admission to world-class universities. Here is a sample question for you. So what we're doing here is taking few concepts together, learning the concepts, and we'll also try to understand how these concepts are tested for an entrance examination to compete. So here is a question for you, which is, for the series 1 minus x to the power of minus 2, where absolute value of x is less than 1, which of the following statements is or are false? False we are looking for, and there could be more than one wrong statement. Now these types of questions are very common, especially for IIT JEE, Indian Institute of Technology, India, joint entrance examinations. So they have this kind of format where more than one could be the correct answer. So let's look into these options. Option A is, the series can be approximated as sum of the series r times x to the power of r minus 1, where r is from 0 to infinity. B, it is a converging infinite series. C, the series can be written as 1 minus 2x plus 3x squared minus 4x cubed plus so on. And D is, sum of the given series is 1 over 1 minus x whole square. You can pause the video, answer this question. To help you answer, I have attached a specially prepared lecture on this topic. You can go through that lecture, which will definitely help you to answer this question. Now, more than that, I'm going to provide you the solution of this question tomorrow, that is after 24 hours. Meanwhile, I would like to see what kind of solutions have you come up with, so don't hesitate to post your answers and solutions. Also, I'm looking forward for a feedback from you. How much do you appreciate this approach? What are you looking for from our website and our channel? And how can we really help you very effectively? These answers will help us provide you with a sustainable solutions for all times to come, and these are going to be free, absolutely free for all times to come. I hope you understand and appreciate it. So now, provide your suggestions and the solution to this question, and tomorrow, that is after 24 hours, I will post a solution, complete solution of this particular question. And then we'll look into question number 2. Thank you, and all the best for your suggestions and the time. I'm Anil Kumar. Welcome to my YouTube channel and the website Global Math Institute. Sharing with you the videos I've understood the requirement of students worldwide. In this video, I'll give an attempt to address higher level mathematics topic, binomial expansion extension. This topic is very important for students taking AP level mathematics, IB mathematics, or International Cambridge plus A plus level. So for any higher mathematics or for first year university, or even getting admission to good universities, for example, taking IIT JEE exam, this will prepare you for that. We'll talk about general binomial expansion, a plus b to the power of n, where n belongs to natural numbers. This is what you normally study under the topic of binomial series. But we'll kind of extend this to include the cases when n is not a real number. Then what happens? So we'll explore what is 1 plus x to the power of n, where n is any real numbers. This series is only valid when the absolute value of x is less than 1, right? So if this value x is less than 1, in that case, you could actually expand this for any real numbers. That means the exponent n need not be just natural numbers. It could be integers or rational. Now that strategy helps us to answer many questions related to questions like approximate square root of any number. Now that is a very important application. At times you need to calculate the square root without a calculator. This can help you. Arranging any binomial exponent in increasing or decreasing orders, writing this exponent in the form of a quadratic equation or a cubic equation may also help to solve many examples. We'll also look into the cases where the number 1 is replaced by any general number a, and then how to implement the same formula. Correct? So let's begin with the binomial series as such. So in general, you know that a plus b to the power of n can be written as nc0 a to the power of n plus nc1 a to the power of n minus 1 b to the power of 1 or b plus nc2 a to the power of n minus 2 b square plus so on. A general term in this series will be NCR a to the power of n minus r and b to the power of r, right? And this series, the last term for this series will be NC0. You start with NC0, 1, 2, 3, 4, it goes to NCn, right? And we have b to the power of n. So that is what is binomial series in general, where we have a restriction that n belongs to natural numbers, right? Some important things which you learned about this series are that there are how many terms in this? Well, there are n plus 1 terms, right? So in this series we have n plus 1 terms, correct? We know n belongs to natural numbers. And the general term, which is right there, NCR a to the power of n minus r br, is actually the term number tr plus 1. Now that is kind of very important to understand, right? Now also let me give you the formula for NCR so that you know and understand what NCR means in this particular expansion. Right, so we have NCR in general as n factorial divided by r factorial times n minus r factorial. That is what NCR is, right? So that is how we see this word NCR. So these are called the coefficients, right? These are the coefficients of our series. You will also notice that the exponents add up to n always, right? So n minus 1 and 1 becomes n. So we also notice here that the sum of exponents is always 1. Always n. Right. So if you add the exponents, you have the sum of these exponents as always n. So these are a few important things to remember as we move forward. Okay? Now let us use this formula to calculate the coefficients, binomial coefficients, right? So when I say we want NC0 value, n factorial divided by r factorial. R is 0 for us, right? So we get 0 factorial times n minus 0 factorial, right? So this is n factorial. And now what is 0 factorial? Well, 0 factorial is 1, right? So this is just 1, and we again have n factorial here. So they cancel, and what we get is 1. So NC0 is just 1, right? Now when I say NC1, that means we get n factorial over 1 factorial times n minus 1 factorial. So that is n factorial over 1 factorial is 1, and we are left with n minus 1 factorial. Now when you say n factorial over n minus 1 factorial, then you get only n times n minus 1 factorial. We get n as a result, right? Now if you have NC2, then the value of NC2 will be n factorial over 2 factorial times n minus 2 factorial, right? So you could write this as like this. Let's show you how to simplify this. N factorial can be written as n times n minus 1 times n minus 2. We can write a factorial here, right? All the terms over 2 factorial times n minus 2 factorial. So this cancels, and what remains is n into n minus 1 over 2 factorial, correct? Now that is how you could simplify these terms and then write them down. So if you continue with this, then in that case NC3 will be what? So we have two terms here when NC2 is there. In NC3 there will be 3 terms. We'll get n times n minus 1 times n minus 2 divided by 3 factorial. So that is how in general you can easily write down the coefficients, the binomial coefficients. Perfect. So that kind of becomes a way, a shortcut method of writing any binomial coefficient. So we'll keep in mind this particular expansion and then extend what happens to a plus b to the power of n if I replace this with, let us say, 1 plus x to the power of n, right? So what we'll do here is, instead of a, we'll just put a number 1, right? And use another number, x here. And we'll see what happens to this binomial expansion when we have binomial expression as 1 plus x. So now, let us explore this particular binomial expression. What we learned earlier, that a plus b to the power of n is basically equals to nc0, a to the power of n, plus nc1, a to the power of n minus 1 times b, plus nc2, a to the power of n minus 2 times b square, and so on. Tr plus 1 is the general term, which will be ncr, a to the power of n minus r times b to the power of r. The sum is always n, right? And the last term will be ncn, b to the power of n, right? So these are our terms. Now in this expression, what I'm doing here is now replacing a with 1 and writing a new binomial expression, which is now for us, let me write in a different ink here, 1 plus x to the power of n, right? So if I replace a with 1, all these a's will vanish, right? So 1 to the power of anything is 1, and when you multiply, you get the same number. So what we get here is nc0, right? And that is 1, right? So here we get nc1, b, instead of b I'm writing x, right? nc1x, plus we get nc2, right? And x squared, plus so on, and then we get ncr, x to the power of r, plus so on. Last term will be ncn, x to the power of n. So we get this particular expansion for our binomial series, 1 plus x to the power of n. The beauty here is that this particular series we just got is actually valid even if n is a real number, right? So the important part here is that this series is also applicable where n belongs to any real numbers, right? So that is the beauty. We are not providing you with a proof here. However, we'll just take this as a statement and explore this further just to show you that it can be used with all the real numbers. The only condition will be that the value of x in 1 plus x, the absolute value of x is smaller than 1, right? So that will be the condition when we could use the series 1 plus x to the power of n as nc0 like this, right? So let me rewrite this in terms of the binomial coefficients. nc0 is just the number 1, right? So it is 1 plus nc1 is n, so we get nx, plus nc2 is n times n minus 1 over 2 factorial x square. Correct? So that is how we have an infinite series here, which just goes on and on. So we use this series 1 plus x to the power of n as infinite series for n being real numbers. Now, does it really work? How do we test it out? Well, we can test it out by using, let's say, first natural numbers. So if I just work out this series for different values of n, let's say we take n as 0. So if n is 0, in that case, what we have is 1 plus x to the power of 0. We know that should be 0, right? Anything to the power of 0 is 1, right? Anything to the power of 0 is 1. So in this series, when we put n as 0, we get 1 plus 0 plus 0 plus so on, right? So it is all zeros, correct? If I use n as equal to 1, then the expression will be 1 plus x to the power of 1, and substituting 1 here, we get 1 plus, then if I substitute 1 for the value of n, then what we get here is x. And then here, if I substitute 1, we get 0, because 1 minus 1 is 0, and so on. For n equals to 2, the binomial expansion will be 1 plus x whole square, and if I substitute 2 here, in that case I get 1 plus 2x, and substituting 2 times 1 is 2, and 2 divided by 2 factorial will be again just 1, and therefore we get x squared here. Now if I have the third term, then it will be n minus 2, right? So the third term will be, let me write down, n times n minus 1 times n minus 2 over 3 factorial times x squared. Let me write down the fourth term also, n minus 1 times n minus 2 times n minus 3 over 4 factorial x to the power of 3 plus so on, correct? So if I continue with this series and write n as equal to 2, then 2 minus 2 is 0, and therefore all the terms will have n minus 2, so all those terms will be 0, right? So we'll have an infinite series, but only there will be 3 terms for this series when the exponent is 2. So that matches with the binomial expansions which we learned earlier, right? Correct? So if I write n equals to 3, we get 1 plus x to the power of 3, and if I substitute 3 here, for n we get 1 plus 3x plus 3 times 2. 3 times 2 is 6, 6 divided by 2 is again 3, so we get 3x squared. And here, when I substitute 3, then I get 3 times, this is 3 times 2 times 1 divided by 3. So what we get here is all 3 times 2. So let me write down like this. 3 times n minus 1 is 2 times n minus 2 is 1 over 3 factorial, which is 3 times 2, right? X squared. Plus, when we substitute 3 here, we get 3 times n minus 1 is 2, n minus 2 is 1, and n minus 3 is 0. So you get to multiply with 0, and here you get 4 times 3 times 2 times 1, right? X, we get x to the power of 3. Now, in this particular case, sorry, this was 3, that is 4. Yeah, 4, right? Let me make a correction. This is x cubed here, right? Right. So we get 1 plus nx plus x squared and x cubed and x to the power of 4, correct. So the last term here is 0. So I could always write this as 1 plus 3x plus 3x squared. And here, what do we get? 3 times 2 cancel, and we are left with x cubed. Now if you see, these are the matching expansions, and if you continue, you find that this series is always a series in which we have n plus 1 terms, right? So there are n plus 1 terms, and they terminate, right? So these are not infinite series. They in fact terminate when n belongs to natural numbers, right? Because n minus r will be 0 after some time, right? So all the terms after that will be 0. Do you get this idea? So in case we have natural numbers, we have a terminated series where the number of terms are n plus 1, right? Now what happens when we have exponents which are not natural numbers, right? So we'll see that part now. But in that case, we'll also consider the cases where absolute value of x is less than 1. We'll explain this to you also. Now, let us again explore this series, which is 1 plus x to the power of n. Let me rewrite this first as nc 0 plus nc1 x plus nc2 x squared plus nc3 x cubed plus nc4 x to the power of 4, so on, correct? Now this time we'll try with numbers which are not natural numbers, right? So let me explore this particular series when we have numbers like n equals to minus 1. So if I have n equals to minus 1, in that case what happens? So what we get here is 1 plus x to the power of minus 1. So n is minus 1. So when you expand this, this is 1 for you, correct? 1 plus. Now here, n is minus 1 for you. So when you expand, so what you get here is, let me write this in the other form first. That'll be easier to really get to this concept. So let me write this back into the form of n times, so it is just n times x, right? So n times x plus this is n times n minus 1 over 2 factorial times x squared plus we have n times n minus 1 times n minus 2 over 3 factorial x cubed. Is that clear to you? Plus so on, correct? So it'll be easier for us to now substitute and check. So we'll again now substitute this value. So if I have 1 plus x to the power of minus 1, I really get 1. And if n is minus 1, I get minus x, right? Here if I put minus 1, then what do I get? So minus 1, and that is minus 2, right? So when it is minus 1 and minus 2, divided by 2, so both minus makes it positive, correct? So we get x squared. Plus, here if I substitute minus 1, in that case, what we really get here is we get minus 1, and this is minus 2, and that is minus 3. And divided by 3 factorial gives me 1. So we get x cubed, and then this series this will be negative here, and this series will be expanded with x to the power of 4, and so on, right? So when you have n as minus 1 in the exponent, you get that kind of a series. However, this series is not terminating. Perfect. So this series will be kind of always going on. So what we see here is an infinite series. Right? Now, likewise, if I substitute minus 2 here, right? So if I substitute minus 2 for n, in that case also, what we notice here will be that the series will be, if I do minus 2 here, 1 minus 2x, and let's expand into this. So we get minus 2 times minus 2 minus 1, which is minus 3, over 2 factorial times x squared. And here we get minus 2 times minus 2 minus 1 is minus 3 times minus 4 over 3 factorial, which is 3 times 2 x cubed, right, plus so on. So if you see this, what you really get is 1 minus 2x, and here we have two negatives, which makes it positive, and 3 times 2 is 6, and what you get here is 3x squared, right? So this 2 cancels, and we're left with minus is plus 3x squared. Now here we have 3 times 2 cancel, that becomes positive, we're left with negative 4x cubed, right? Plus so on. So this series is again not becoming 0. It is an infinite series. Do you see that part? So what we notice here is that the series actually expands. So if you try for 1 minus x to the power of minus 3, do the same calculations, what you will get is 1 minus that nx is minus 3x plus minus 3 times minus 3 minus 1 over 2 factorial, right? Plus minus 3 times minus 3 minus 1 times minus 3 minus 2 over 3 factorial, and so on, right? So what you really get here is 1 minus 3x, and here minus 3 minus 1 is minus 4. So that divided by 2 is minus 2, and so you get minus and minus is plus 6x squared, sorry, and that is x cubed, okay. So 6x squared, and here we'll take a negative term, and the value will be, this is 3 times 2 here, right? And in the numerator, we have minus 3, and then minus 3 minus 4 is minus 4, right? So that gives you 2 here, and minus 3 minus 2 is 5, multiplied by 2 is 10. So we get 10x cubed, right? Plus so on. So what you notice here is that there is an infinite series, right? Now this series is in the decreasing values of these magnitudes, right? So what do you notice here? If the absolute value of x is less than 1, then this series is decreasing. In this part, we discussed that n could take any real value. We just took negative 1, negative 2, negative 3, and we did find that you can have an expansion where if the absolute value of x is less than 0, we get decreasing terms. So we have a converging series whose sum can be found, right? So let us summarize this and then move forward. So once again, what we saw here is that this infinite series, 1 plus x to the power of n, where x is less than 1, we did see that for different values of n, which is like minus 1, minus 2, minus 3, minus 4, we do get a converging series, right? So we get a converging infinite series, right? So let me write down, copy from here what we really got these series as. Now these are very important series to consider, right? So we have 1 plus x to the power of minus 1, and that can be written as, we got this as alternating plus and minus, right? So we have 1 minus x plus x squared minus x cubed plus so on, right? Now if I have 1 plus x to the power of minus 2, in that case, the series obtained was 1 minus 2x plus 3x squared minus 4x cubed plus so on. And if you have 1 plus x to the power of minus 3, then the series obtained in this particular case is 1 minus 3x plus, so alternately we get plus and minus, right? 6x squared minus 10x cubed plus so on, correct? So likewise, we get the series where, as you can see very clearly, if the absolute value of x is less than 1, right? Sorry, is less than 1, in that case, we know that x is greater than x squared, which is greater than x cubed, right? And we also see that x to the power of n, as n approaches infinity, approaches 0, right? So it becomes lower and lower value. So we have a converging series. You understand now, right? So if we have negative powers, in that case we do get converging series. You can explore with what happens when we have powers as rational numbers. Let's say what is 1 plus x to the power of half, correct? So this series is also converging provided the value of absolute value of x is less than 1, correct? So let's try to explore this in the next part of the video. So now we have 1 plus x square root, right? Now this is a very important series since we can actually estimate the value of square roots with the help of this particular series. Now this could be written as, we could also write this as 1 plus x to the power of half, right? And we are going to consider that the absolute value of x is less than 1, correct? So when x, this series will be what? 1 plus x to the power of half. We can write this as n1 plus nx, the formula is 1 plus nx, plus n times n minus 1 over 2 factorial x squared plus n times n minus 1 times n minus 2 over 3 factorial x cubed plus so on, right? Now since the power is half, we'll replace n with half in this particular series and see what do we get. So we get 1 plus half of x, right? Plus this is half, so we get half minus 1 over 2 factorial, which is 2, x squared, plus we have here half times half minus 1 times half minus 2 over 3 times 2, x cubed, plus so on, correct? Which is 1 plus half x plus, now this is half minus half is minus half, right? So we have minus 1 by 4, half times minus half over 2 x squared, and here we get half times half minus half is minus half, and half minus this is minus 3 by 2, right? Over 3 times 2 x cubed plus so on, correct? So we get 1 plus half x, and here we get minus 1 over 8 x squared, and here we get minus and minus becomes plus. So we have 1 times minus 3, that is 3, over 2 times 2 is 8 over 3 times 2 x cubed, right? So I could write this as 1 plus so on, correct? So all these terms are very, very small as we go on, right? So we have 1 plus half x minus 1 over 8x squared. And here 3 and 3 cancel, and we get 1 over 8, and this becomes 16. So we get 1 over 16x cubed, plus so on, correct? So when we have this series with the power as half, we could actually write this as approximately 1 plus half x minus 1 over 8x squared plus 1 over 16x cubed, and so on, correct? So that is how we get this series. Now this series really helps us to approximate the values of square roots. Now to approximate to 2 decimal places, we could just use the first 3 terms. We get to 2 decimal places, and if you want to get to 3 decimal places, we could use the 3rd term also, the 4th term also, correct? So that really helps. So what I would like you to do is to calculate the square root of 101 using this particular expansion of 1 plus x to the power of half, correct? How are you going to do it? Well, think about it like what? You could write square root of 101 as equal to the square root of 100 plus 1, right? Now, 100 square root is known to you. So what you can do here is that you can take 100 common, right? So you get 1 plus 1 over 100 within square root. Now that gives you 10, and then within the square root you get 1 plus 1 over 100. Now, indeed, the x value, which is 1 over 100, is much smaller than 1, and therefore the formula can be used, right? So now apply the formula. Expansion. And calculate, right? So I leave this for you to calculate. I hope the concept is clear to you. You can even use just these 3 terms, right? So you get 10 times 1. Now, this part of square root is 1 plus half x minus 1 over 8x squared, right? So when you substitute, you'll get the answer for square root of 101, correct? So I'm leaving it here for you to explore. Perfect? We'll get back to such questions later. Now, let's move on and take some more examples. Now this time we have a question, and instead of half, we have minus half in the exponent. And we have a term 1 plus 2x to the power of minus half. Your question here is to write this in expanded form, right? So this basically is kind of like this, 1 over square root of 1 plus 2x. Do you see that? Now we have to write this in expanded form using the binomial expansion. So basically, we know the formula, which is 1 plus x to the power of n, can be written as 1 plus nx plus n times n minus 1 over 2 factorial x squared plus n times n minus 1 times n minus 2 over 3 factorial x cubed plus so on. Now these terms are very small, so we can just leave them. In our case, we have 1 plus 2x to the power of minus half. Do you see that? So we have minus half. So n will be replaced by minus half, and x will be replaced by 2x. Do you see that? So we get 1 plus, we have minus half here, and x will be replaced by 2x. So that becomes our second term. The third term will be, we are replacing n with minus half, so we get minus half within brackets, we have minus half minus 1 divided by 2 factorial, and this x will be replaced by 2x whole square plus so on, correct? So this is minus half times minus half minus 1 times minus half minus 2 x cubed. X is replaced by 2x, so let me write 2x whole cube, okay, divided by 3 factorial, right? So that gives you 1, and minus half times 2x is minus x. And here we have minus half, and that is minus 3 by 2. So it becomes positive. So we have a positive half times minus 2 and minus 3 by 2. Both negatives becomes positive over 2 factorial, correct? And then we have here 2x whole square, which means 4x square, correct? Now here we have, there are 3 minuses. This is negative, this is negative, this is negative. We have 3 minuses, correct? So this sign will be negative, and we have here minus half. Oh, sorry, no need to write minus half now. This times 3 by 2 times 5 by 2, correct? With a negative sign. Everything over 3 times 2. And we have 2 to the power of 3, which is 8x cubed. Right. Now this can be written as 1 minus x, and that is 1 times 3 is 3 over 8 times 4x squared. We'll simplify this now. Minus, so these are 8, right? So you can write this in the denominator, 8 times 3 times 2. The numerator here is 3 times 5, and we have 8x cubed plus more terms, right? It is definitely an infinite series, right? Now this could be written as 1 minus x. That goes 2 times, so we get plus 3 by 2 x squared. Now here we can cancel 3's. We can also cancel 8. So we get 5 by 2 minus x cubed plus so on, correct? So we could actually write this as a cubic equation. Do you see that part? So that becomes a cubic equivalent of our radical function approximately. Does it make sense to you? So that is how we could actually write this. So this expression is now equal to 1 minus x plus 3 by 2 x squared minus 5 by 2 x cubed, right? So plus so on, but these are your significant terms which could help you to evaluate the value of 1 plus 2x to the power of minus half without calculator. Do you see that part? Now, in these expansion, you should note that the value here, which is 2x, the absolute value of 2x should be less than 1, correct? That means what? That means that the absolute value of x should be less than half. So for this expansion to be utilized, it is necessary that the absolute value of x is less than half. Otherwise, you cannot use this expansion for evaluating approximate values of 1 over square root of 1 plus 2x. I hope that makes sense. With that note, let's move on and take up this time example on cube root. Okay. So here is a test question. Now these are actually the test questions seen in many competitive exams. You need to write quadratic approximation of cube root of 1 minus 6x. Note, in this case, we have the value of n as 1 over 3, and the value, which is, I should write the inside value, is minus 6x, right? So that is the other value to work with. Okay. So let's see what do we get. Now we know the general formula, which is 1 plus x to the power of n is basically equal to 1 plus nx plus n times n minus 1 over 2 factorial x squared plus n times n minus 1 times n minus 2 over 3 factorial x cubed, correct? Plus so on. Now, this expansion which I am doing here is only valid if the absolute value of 6x is less than 1. That means the absolute value of x is less than 1 over 6, correct? Now within that domain, we get the expansion which we are talking about. Okay, so now if I write this, which is 1 minus 6x to the power of 1 over 3, then what do we get? So in this case, let me use the different ink now. We'll expand and see what do we get. So we get 1, n is 1 over 3, so we get plus 1 over 3, and the value of x is replaced by minus 6x. Okay, now this time we get 1 over 3 times 1 over 3 minus 1 over 2, and here we have 6x whole square. Now plus 1 over 3 times 1 over 3 minus 1 times 1 over 3 minus 2. This is x cubed over 3 times 2. That is 3 factorial plus so on. Correct? Now that gives you 1 minus 2 times x. Now this is, if I take this 3 here, so we get minus, okay. So 3 minus 1 is 2. So we get 2 over, let me write in 2 steps. 1 over 3 times, minus I have already taken outside. So 3 minus 1 is 2. So we get 2 over 3. Let me write this as half here. And 6 square is 36. X square, right, plus. We have this term now. So which is 1 over 3 times minus 3 minus 1 is 2, so we get 2 over 3. 6 minus 1 is 5, so 5 over 3 times, this is 1 over 6, right? 3 times 2, x cubed plus so on, correct? So, okay, so here we get 1 minus, because that becomes positive. Now, wait here. This was minus 6, sorry. This is minus 6 whole cube, right? So we do have a negative 6 here. So we have 1 negative, 2 negative. This one is negative. I missed the term minus 6x cube here. So we'll write minus 6 whole cube, right? That is the term which I missed. Okay. So what we get here is 1 minus 2x, and this is 36. So 3 times 2 is 6. So it goes 6 times, and 6 times 3 is 18, so that gets 2 times. 2 times 2 is 4, so we get 4x squared. Okay. Now in this case, one of the 6 cancels. We have a negative term because of this being negative, and we have 5. That 6 goes here, so we will rewrite this. So 3, 3, 6. So we are left with 36, and divided by, let's do it like this. We have 2 times 3 as 10, and then we have 36. This 6 cancels, right? And we have here 3 times 3 times 3, x cubed. Right? We'll do it in 2 steps. Okay. So we get 1 minus 2x minus 4x squared, and that is minus. So we get 9 times 4, right? So we get 40 over 3 x cubed, right? Plus so on. So we could actually write this expression as a cubic expression as shown here. Perfect? Does make sense to you? Right? So that is what we could do with these types of expressions. I hope that makes sense, right? So in this exercise, we learn how we could actually write our expressions in different forms, and we could also work with the cube roots, and when the power inside is negative, as we have seen in this particular case, right? So that's what is this expansion very helpful. So here we have a question, and that is to write in cubic form. So that is your cubic form of cube root of 1 minus 6x. Do you see that part? So that could be asked as a cubic form of cube root of 1 minus 6x. Let's take another question based on this. Now what we have here is we need to explore a plus x to the power of n, where n belongs to real numbers, So in binomial expansion, this was natural numbers. Now we are actually extending the binomial expansions, and we just saw many examples where a was 1. Now in this particular case, we have a special case. We are writing 2 minus x to the power of minus 3. That minus 3 is not a natural number, it's a real number. So I'd like you to pause the video and take this as a test question. Correct. Try to answer this. Now how should you do this? What we really know is that 1 plus x to the power of n is equal to 1 plus n times x plus n times n minus 1 over 2 factorial x squared plus n times n minus 1 times n minus 2, which is nc2, 3 factorial x cubed, right, plus so on. So that is what we know. Now in our case, in this particular expansion, what we need to do here is we have to first step write this in this form of 1 plus something. How do we do that? Okay, so we could do like this. We have 2 minus x to the power of minus 3, right? So we can take 2 common. So we can take 2 common. So we get 1 minus x over 2 to the power of minus 3. And that could be written as 2 to the power of minus 3. And within brackets, we do get 1 minus x over 2 to the power of minus 3. Does it make sense to you? Right? So that becomes the function for us to expand. And definitely, this is valid for x by 2 to be less than 1 or x is less than 2, absolute value of x. So that becomes a restriction on this particular thing. Correct? So I hope that makes sense, right? So now let's look into this. 2 to the power of minus 3 is 1 over 8. So what we have here is 1 over 8, and within brackets we have 1 minus x by 2. We are looking for minus 3 power, and that's the expansion. So not very difficult. So we'll write 1 over 8 here outside, and we'll replace n with minus 3. So we get 1 minus, I will write plus here, and we'll write minus 3 in the brackets. And then for x as minus x by 2. Perfect. That becomes the second term. The third term will be n is minus 3. So we have minus 3, minus 1. And here we have 2 factorial. So which is right there. X is minus x by 2. Right? Whole square. Like this, we get so many terms. We'll just work out 3 terms in this case, right? Bracket close. It's definitely infinite series, which is converging when x is less than 2. So we get 1 plus, that becomes positive, 3x by 2. Now this is minus minus, and that is also positive, okay. So that is, we get 3 times, this is minus 4, and these 2 2's is 4, cancel, right? So we get minus 4 cancels, we can left 3 here, so 3x squared, right? So that becomes the part, right? Plus so on, correct? So that becomes the equivalent expression for the given expression. You can always extend it and get the next term. I hope that makes sense. So in short, what we have learned here is that you could write any expression which is of the form of a plus x to the power of n as equal to a to the power of n, and within brackets you take a common, right? 1 plus x to the power of n, x to the power x over a to the power of n. What I wrote here is a to the power of n is taken outside, and within the brackets we get 1 plus x over a to the power of n, right? Now in this particular case, all these expansions are possible if x over a absolute value is less than 1. Or you could say the absolute value, you could say that the absolute value of x is less than a, right? So that is when you can use all these expansions. So I hope with this you understand the concepts of how we can really expand the binomial series and utilize it for real numbers. Perfect. So, in short, we started with the binomial general series, which is only valid for natural numbers. However, we could treat this as 1 plus x to the power of n and so special that it could be extended for all real numbers provided absolute value of x is less than 1. This series helps you to calculate the values of square roots, nth roots, and many other related questions. It also helps you to arrange the binomials in ascending or descending orders, and at times we could have many related questions in the test paper. So a simple series modified, a very important series modified into a simpler expression becomes so versatile that it can be utilized in many different ways. So I hope this video gives you a good understanding of the topic. Feel free to write your comment, share your views, and if you like and subscribe to my videos, that'd be great. Thanks for your time and all the best.